Stop worrying about homework and start learning with confidence. This is AskLearn. Complete help for every subject. Like, share, subscribe for daily learning videos.
In this problem, we have a charged particle heading due east. It's going to encounter a region of space with a particular magnetic field, and in traveling perpendicular to it, it's going to do a 1/2 circle and head the other way it came. So what does that look like, right? So we're going to have some region of space with our magnetic field in it, and our particle is going to enter that region, going a particular speed. It's going to travel along a circular path of a particular radius, and then, of course, head back with the same velocity in the opposite direction. And we have the radius of our circle represented by this line here. Now, what do we want to find out here actually is how long that this particle is traveling in this semicircle, half of a circle. So we want to find out the delta t. Now, how do we figure that out? Well, we go back to an old idea in physics, especially physics 1, the idea of how velocities, distances, and times relate to each other, right? So as this particle is traveling around this semicircle, right, it actually travels a distance equal to half the circumference of the circular path that it travels. So the total distance that this particle is going to travel, we'll call it little d, right, is going to be half the circumference of the circle that the particle travels through. Now we know circumferences of circles are given by 2 pi r, so we divide that by 2, and we see that the particle is going to travel a distance of pi multiplied by r. Now remember, the particle travels a constant speed of v throughout this entire path. So if I wanted to know how fast that was, right, I would take how far the particle traveled, in this case, this distance d, or pi times r, and divide it by how long it took. And that would tell me the speed of my particle. That's some ideas back from physics 1. So if we want to find out how long the particle spends on this semicircular path, then we just need to find out how far it went, and then divide it by how fast it's going. Well, we know how far it went because it's just pi times the radius, and we at least know an expression for the radius of the circular path that this particle is traveling. So that, of course, is given by r equals m times v divided by the absolute value of q naught multiplied by the magnetic field through which this particle is traveling. So I can then get an expression for d that is equal to pi times r, but r is all of this stuff, right? So we have pi times mv divided by q naught divided by b. Right, now I just need to plug this into my time difference equation, which is d over v. I'm going to leave my 1 over v here and multiply by d, which is mv, pi mv divided by q naught multiplied by b in the denominator. And now you'll see what's nice is the velocity that we do not know cancels out and goes away, and that often happens in our physics problems. Things we aren't given or cannot find just cancel out. So ultimately, the time it takes for this particle to travel along the semicircular path is given by pi times the mass of the particle divided by the charge of the absolute value of the charge of the particle, and then again divided by the magnitude of the magnetic field through which the particle is traveling. So we know all of these values. Pi times the mass is given as 6 times 10 to the negative 8 kilograms. I'm going to divide that by our charge, which is 7.2 times 10 to the negative 6 coulombs, because it's 7.2 microcoulombs, and the magnetic field through which this particle is traveling has a magnitude of 3 teslas. We plug all that into our calculator, and we see that it takes 8.7 times 10 to the negative 3 seconds, or 8.7 milliseconds, for this particle to follow that semicircular path to head due east and then turn around and head due west.